thank you. Yeah, my name is Matti Hellström. I work as the product manager at SCM, and I'm very happy to be able to give this webinar about the new features in Amsterdam Modeling Suite 2023 that we released just a few weeks ago. And this is the result of a lot of hard work of both myself, but also all my colleagues at SCM, and also all the academic collaborators and contributors that develop new methods and new features and contribute those to our software. So the goal of the Amsterdam Modeling Suite is to make computational chemistry work for you. And so we have a very broad set of tools and many new features in this new release. And there are too many to talk about, but you can find the link to the full release notes here. But even the full release notes are actually quite abridged. So if you scroll down a bit per module, you can then also click to find even more details about what's new in the various engines or the AMS driver or products. And just to kickstart things, what you've been looking at here while I've been speaking is a type of metadynamic simulation for conformer search. So this is the CREST method by Stefan Grimme, conformer rotamer ensemble sampling tool. And what's new in this release is that, well, you can use this method with any of our compute engines. So you can use, for example, the GFNFF force field by Grimme, or also, like in this case, with machine learning potentials. So that's quite exciting. I'll get back to the conformers a bit later. So in general, I assume that most of the listeners are familiar with the Amsterdam Modeling Suite and what it is, but just in case you're not, here is a slide. So it's a suite for computational chemistry, and there is molecular DFT, there is periodic DFT, tight binding methods, force field methods, and that includes then normal force fields, sort of like GFNFF or GAF, reactive force fields like ReaxFF, machine learning potentials, and also this AMP force field that I will talk a bit about later as well. Further up the multiscale ladder, we have some various tools for kinetics, like kinetic Monte Carlo and microkinetics, and we also have fluid thermodynamics, so especially then COSMOS to calculate things like activity coefficients, solubility, and so on. All of these tools are supported by a graphical user interface and by Python scripting workflows. So no matter what type of work you like to do, you can either use graphical user interface or the Python scripting. And I'll show you a bit of Python scripting at the end of this talk as well. So here are some of the new features. So that I'll just briefly mention in rapid succession. So there are some new features for excitations and charge transport, new methods or functionals in ADF. There's the M2GNet machine learning potential that's new, and together with the ANI2X, that it's not new for this release, but now we have two of these quite broadly applicable machine learning potentials, so they can be used to great effect. There are news in the conformers that I mentioned. There's the AMP polarizable force field for electrolytes and polymers. ACE reaction network is a way to quickly generate reaction networks to find out reaction mechanisms from a set of reactants to products. We have some new features for the multiscale modeling of heterogeneous catalysis. Yeah, this goes all the way up to the computational fluid dynamics reactor scale. Yeah, I'll describe the details a bit later. We have many new features in our parametrization module ParAMS for ReaxFF and DFTB parametrization. We also have two new engines. So one new engine is ASE calculators, and I'll explain what that is a bit later. Basically, it's an interface to external codes. And then we have a new engine, Quantum Espresso, in an alpha version, and I'll also explain what the benefit of that is. And finally, I'll finish up with some Python tips. So actually, the Amsterdam Modeling Suite is often quite convenient to use from Python, and I'll just show you how to do that in case you're not familiar with it. And you can find the full release notes at this link, scm.com/2023. So let's get started. Excitations and charge transport. So yeah, there are a few things. So one is this OLED workflow, which is a feature in our workflows module, where what you try to do is you try to build a realistic stack of OLED molecules like the ones you see here through deposition simulation. So similar to this physical vapor deposition that you kind of see here, very much sped up, and so you build up layers and layers of it until you have a very large material. And then for each molecule in this huge slab of amorphous OLED molecules, you calculate the properties and the distribution of properties like ionization potentials, electron affinities, and exciton energies. And what's new in this release is, for example, that is, well, the results are more accurate, but you also can do this deposition a bit faster with the GPU acceleration by combining it with LAMS simulations. Another new feature are excitation areas with the quasi-particle self-consistent GW-BSE. So this is work from Arno Förster and Lucas Fischer at the Free University Amsterdam, where you can do these very accurate excited state calculations quite quickly. And you can also combine that with spin orbit coupling. So that's in a separate article that is in progress. So Arno actually gave another seminar on qsGW-BSE not so long ago that you can find on our YouTube channel. Okay, new methods and functionals in ADF. So there are two that I highlight here. The first one is R2Scan3C from the Stefan Grimme group. So here I have some quotes from the abstract. So it's reliable, robust, and accurate, and on par with or more accurate than the hybrid AMS6 D3 TCP function. So also here, Thomas Gasiewicz, the first author of this paper, gave a webinar not so long ago that you can find on our YouTube channel if you want to find out more about this method. And another new functional is the sigma functional, or the scaled sigma functional, where the abstract, the accuracy of 1 kcal per mole in reaction or transition state energies. And what you want to look at in this histogram is the red bar, and you want the red bar to be as low as possible. So low is good, and then the different letters here are different types of benchmarks that they have tested. So you can see that the scale sigma functional perform really well. So we also have that now in ADF. So that's work by the Andreas Gerling group. Moving on, we also have the M3GNet machine learning potential. So this is by Xue in San Diego. A universal graph deep learning interatomic potential for the periodic table. So it's not the entire periodic table, but most of it. And it's actually very good. So I'm always amazed when I use this machine learning potential, how good it is, how reasonable it is. It's not perfect, but it's quite incredible. So yeah, it's been trained to materials project data, so PV and PV plus U. So there's no dispersion built into it. So if you need dispersion, like for maybe you have a naphthalene crystal like we do in one of the tutorials, then you can add Grimme D3 or D4 dispersion corrections to that. And so it's a kind of universal potential for materials. And what can you do with this? Well, mainly you want to calculate equilibrium properties, so equilibrium structures, equilibrium lattice parameters, equilibrium energies. It sometimes also works for things like transition states, but it's not really the main focus of it. It doesn't work for things like radicals and so on. So it's mainly geared towards materials, both inorganic and organic materials. So here's an example that we did here at SEM for lithium average intercalation potentials with M3GNet comparing to experiment and DFT for different type of lithium metal oxides. But as always, this is machine learning, so do not blindly trust the results. If you throw something at it that it hasn't seen before, it will try to do something. But you always need to be a bit careful about the results. So now we have the M3GNet potential in AMS2023, and that complements quite nicely the previous one we had, the ANI2X potential by Isaev and Reutberg. So this M3GNet is very nice for materials, and the ANI2X is very nice for organic molecules, drug-like molecules. That for example, to score conformers, you can do that very accurately with ANI2X. Okay, moving on to conformers. So the conformers tool has been redesigned a bit. So now it's more general. You can generate the conformers with 2 different methods. And if you're not familiar with conformers, they are the same molecule, but the dihedral angles are rotated in different ways. Then you get different conformers, and they might have different energies, like you see here on the right. So here, the conformer number 1 here is the lowest energy conformer, and then number 2 has a bit higher energy, and number 3 has an even higher energy, and so on. And so you can generate these now with 2 different methods. One is the RDKit method that comes with the RDKit, so that's an open source cheminformatics package. or you can use this CREST method by Stefan Grimme. And either of these methods, you can now combine them with any of our engines. So for example, the ANI2X I mentioned, or the GFNFF force field, which is it's very fast for these type of things, and it's very good. A DFTB, or ADF, if you want to score DFT, score them with DFT accuracy, to generate, optimize, and score conformers. And you can also calculate then Boltzmann average properties, for example, IR spectrum. So I'll take a quick break from this little overview and just show you two examples in our graphical user interface on what this can look like. So the first is the M3GNet potential, and so you in this ML potential, or in this yellow dropdown in AMS input, you can select ML potential. In this dropdown, you select M3GNet, and then you can either submit this as a normal job, or you can, for example, click this pre-optimize button. So here on the geometry optimization panel, I also tick the optimize lattice. So if I click this button, hopefully, so M3GNet, it has a bit of a startup time. But once it gets started, it's very fast after that. So let's see if it goes well. All right. There we go. And so I had, I deliberately distorted this structure to begin with, because the M3GNet structure is very close to the PB calculated structure. But now we have optimized this lattice. We can get the energy. Or we can also go to this lattice page and look at the lattice parameters. One quick little tip for you is that if these lattice vectors are not, there are 3 components for every vector, which is a bit awkward to work with. So what you can do is if you tick this little box there, and then you can align, for example, A to the x-axis, and then you will get the 3 components being 0. It's a bit nicer to work with. And this is a zeolite material that I just picked from literature to see if M3GNet will work on it, and it does. The second thing is conformers. So if you generate conformers, so here I have this molecule that I showed, and I generated this with CREST and GFNFF, and then I re-optimized them with DFTB, and so I get the 122 conformers within 0.13 electron volt. And they look like this. And then what you can do is you can calculate Boltzmann average properties like IR spectra, for example. So that's what I have here in this spectra. So then we have the calculated IR spectrum, and this is now a Boltzmann average over all the conformers. So if I click on a point here, then we can see here. So let's say take the OH stretch. So that's the highest frequency, right? And we see that if we're at the very highest frequency, the OH is sort of pointing out into the vacuum. But then we have other conformers with this peak where, okay, the OH is sort of pointing into this aromatic group. And then if I go down further, now the OH is sort of pointing into the nitrogen here. And further down, the OH stretch is pointing towards the sulfur. So depending on which conformer you have, the vibrational frequency of this OH stretch will be very different, right? And this is a Boltzmann averaging, so depending on how stable each conformer is, it will have a certain weight to the spectrum. So unfortunately, my mouse just ran out of batteries, but I'll keep going anyway. So for example, if it's like uniform averaging here, then now there are very many conformers, so it takes a while to do this. But then you can see that the spectrum changes. So now each conformer is weighted equally, but that's usually not what you would want. Let's do Boltzmann averaging, and then of course you can also set the temperature. So if you decrease the temperature here, you will increase the contribution from the lowest energy conformer. So if I say 30 Kelvin, then the spectrum looks like this instead. So that's quite a significant change. Okay, let's move back to the presentation. So CREST is very thorough. it's also generates a lot of nice conformers and performs very well. And it's also the method that we use ourselves for this type of thing, or our preferred method. Moving on, we have the AMP polarizable force field, and so this force field was technically part of AMS 2022, but we have now improved it a lot, both in terms of usability and also in terms of the atom typing. So it's now usable for more molecules. And this AMP force field is a collaboration with Wasatch Molecular in the US. It's a non-reactive force field, but it has automatic atom typing. So if you put in your molecules, you can just it will figure out what the correct atom types are automatically. And so it works for many different types of molecules. It works for organic molecules like amides and esters, many different types of solvents, so nitriles, carbonates, sulfones, and so on. It also works for ions, and that's actually a great feature of this force field, is that you have the correct electrostatics. And so in particular, you can model lithium ions, but also many other types of cations and also the anions. Right? And this works for both then electrolytes, and also you can also model polymers with this force field. And so we have a tutorial now on how to calculate the viscosity. So I'll just show you this trajectory in the AMS movie. So this is from our tutorial, and okay, it's a normal MD trajectory run at constant temperature. And what you can do is you can extract the off-diagonal components of the pressure tensor for this simulation, calculate the integral, and then fit the curve to the resulting output, and the limiting value there will be the viscosity. So that's what you see here. Sort of the blue curve is the raw result, and the red curve is a type of fit to it, and then you can extract this eta, which is the viscosity. Moving on, ACE reaction network. So this is from a collaboration with the Woojun Kim's group in Korea. And so this is a method to quickly generate and minimize reaction networks. So if you have a few molecules and you know they will produce some other molecule, but you're not sure about the reaction mechanism, then this method will sort of brute force it almost. It's not quite brute forcing, but it will figure out how many bonds to break, or how many bonds need to break, how many bonds need to form, and sort of minimize the path to do that. And so this is also supported by the graphical user interface. So you can do that to find reaction mechanisms, for example. Okay, multiscale modeling for heterogeneous catalysis. So SCM has coordinated the ReaxPro project, which is a European project for multiscale modeling on heterogeneous catalysis, where the goal is really to bring these different scales together, from the DFT up to the nanoparticle scale with the kinetic Monte Carlo and microkinetics, and all the way up to the computational fluid dynamics on the reactor scale. And so you know, AMS, we mostly work down here at this scale with DFT and force field, where you sort of have control over the atoms. We have now also integrated functionality from this EON code by Hannes Jönsson in Iceland, and Graham Henkelman in Texas. And so you can then generate reaction networks, for example, on a surface like this, and then you can feed that into the kinetic Monte Carlo code Zacros. So we collaborate with Michael Stamatakis at the University College London, who developed the Zacros code. So all of this you can now basically do in a single unified workflow. And then we have one new feature now in AMS 2023 is that you can fit a machine learning model to the output from Zacros simulations and use that as input into this catalytic foam code to do the reactor modeling. So catalytic foam is not yet, it's not part of the Amsterdam modeling suite, but you can get the AMS driver, these types of reaction networks, and Zacros through SCM. Okay, ParAMS for ReaxFF and DFTB parametrization. So I'll actually start running ParAMS first. So I'll just open the ParAMS GUI, and this is now taken from one of our tutorials. It's how to the goal of the tutorial is to train a force field for the for zinc sulfide, and so there are different types of training data that are imported, and if you've never seen ParAMS, you might be a bit scared of this this interface. It might look a little bit crazy, but everything is under control, and so you can select which parameters to optimize and the ranges of values. Yeah. And one new thing that we do now in 2023 compared to 2022 is we have a new type of input that's a little more user-friendly. And one of the biggest things is that you can run multiple optimizers in parallel. So if I do that, so I start running it, and yeah, you always hope that it will work. I'll get back to that soon, but then what you see here is from one of our tutorials that you can run multiple optimizers in parallel, and if they converge to bad solutions, you can stop them either manually, or you can set up basically pieces of code that will detect when an optimizer is not performing well, or when it's not performing as well as another optimizer, and then you can stop it and start at different points and so on. It's actually quite amazing functionality. If you use ParAMS a lot, then you can really benefit from this. So here we see we're running, and the goal, right, is to minimize the loss here. So the loss measures how good are my parameters, and I want them to be as good as possible. So I want the loss to be as small as possible. And so all four of these seem to be doing a pretty good job. But let's now say that the black one is optimizer number one. Let's say I think this is the worst one. I want to stop it. And I can go to File, and I can say Stop Selected Optimizer. And I want to stop optimizer one. And then you can see it gets this icon. So now it's been stopped. And then what will happen in a few seconds is it will start another optimizer, the blue one here, and continue, right? And you can set up that it will continue, you know, should it start from the same point as the previous one, or should it start from the best current one, and so on. It's amazing features for ParAMS. So I will stop that job now and continue with the next bit of ParAMS. Main new feature is the parameter sensitivity analysis. So this is work that I was involved in myself, actually, in this paper that was published this year, together with Tom Verstraalen and Michael Gustavo. And yeah, you saw the list of ReaxFF parameters. It can be a bit daunting, but this tool can help you select which ones to optimize and only optimize those, and then you will converge faster, basically, to a good solution. And so what you see here on the right is yeah, different parameters in ReaxFF and this calculated sensitivity. So what we would say is we would say you really only want to yeah, optimize the most sensitive ones, and that's also what we demonstrate in this paper. Okay, another new feature is the atomic simulation environment. So if you don't know what this is, it's a type of Python package, or yeah, a community that yeah, so that you can execute computational chemistry codes from Python. And of course, we have our own way of doing that with the PLAMS Python library. But this is quite popular and many people have workflows that use this and so on. So now we're actually completely compatible with ASE. So if you're used to using ASE, ASE tools like the ASE-MD, or maybe some genetic algorithm that is built on ASE, or maybe you run IPy for path integral molecular dynamics, then you can use this ASE calculator for AMS, and that gives you then access to all of our engines together with the ASE tools. Or also the other way around, and that's what I'll show next, is that we have our AMS driver, where we can do, for example, transition systems, molecular dynamics, conformers, PES exploration, a lot of different things. And then we can use any existing ASE calculator. So if you're using an ASE calculator to run some external code and you want to hook it up to the AMS driver, then you can now very easily do that. So I'll just briefly show that. So here, for example, in this yellow dropdown, I choose ASE. And then, yeah, you can set any calculator you want. So I'm going to use this EMT calculator, which is a quick force field that they have built or implemented into ASE. And I'll run a PES exploration or a process search. So if I run this, yeah, let's see what happens if we manage to find any state. With this PES exploration or the process search is always a bit random what you get. But there we go. So okay, we started from state 1 here, and now we found a transition state that looks like this, and then a second minimum that looks like this. So it's yeah, I can't easily rotate this molecule now because my mouse isn't working. But yeah, this will then basically continue and continue, and then you find more and more states. And you can use this with any engine then. So any calculator from ASE or any of our own engines like DFTB or Heterogeneous, like I tried here. So let's maybe see what that one is. Yeah, you find all of these different states, and that includes both minima and transition states. Okay, so that's just a bit of fun. So you can use these ASE calculators. And if you don't know what ASE is, you can probably ignore that feature. So it's yeah, mainly if you are familiar with it already and use it to run Python calculations. Second to final point is Quantum Espresso as an AMS engine. So this is now a sort of an alpha release or command line interface to this. So it's sort of like what I showed with the ASE calculators, but yeah, with Quantum Espresso. So the goal here, or the reason to do this, is to expand the Quantum Espresso functionality to all the AMS driver tasks. That includes, for example, then transition state search, PES scan. You could also do this PES exploration that I showed. You can do conformers, maybe, or anything you like. And yeah, this is, if you already are familiar with Quantum Espresso and you prefer Quantum Espresso for some reason, then I think it's quite a nice feature. Of course, this is all possible with our own DFT code band, right? And so here I show this example PES scan for an oxygen atom diffusing on a surface. So you go from on top to the FCC site, to the bridge site, to the HCP site, and back to on top. So I can just show you that in the AMS movie. Here it is. Yeah, so this oxygen atom is sort of diffusing on the surface, and you get the energy as a function of this coordinate. And yeah, from this you can extract barriers and feed them into microkinetics, for example, or kinetic Monte Carlo. Okay. I'm moving quite quickly, but I have a lot of material to cover. So finally, then I just want to give you a few Python tips. Sometimes it is quite convenient to run jobs with Python, and so if you're not familiar with it, you may wanna try it. We've made some efforts now in this newest release to make it even easier to run. So for example, we now have Jupyter Lab that you can install through the package manager. And I'll just show an example here, right? So you can build, show pre-optimized structures, run simulations, and then you can plot the results through just launch AMS movie if you prefer to view the results in our own graphical user interface, right? So AMS movie or AMS Spectra or AMS View and so on. So let's try that. Let's just see what happens if I start this. So here I start Jupyter Lab, and I will actually start a new one. And then I import the PLAMS library, and I call this init function. And then what you might want to do is you might want to create a molecule, right? So I usually use the Smiles code for a molecule like ethanol. So then we can plot this molecule. So this uses actually an ASE plotting tool behind the scenes, but okay, we have ethanol. If we want to print the coordinates, we can just get the coordinates. And then what's great is that you can also say optimize this molecule instantly. So you can say molecule equals pre-optimized molecule. Let's say you want to do UFF. And then we want to print the coordinates. Yeah, Okay, so now I optimize this molecule with the UFF force field, and the coordinates are different. If I want to do GFNFF, I can do GFNFF, and now it's the GFNFF optimized structure. Okay, so that's nice. And now let's build a box of these molecules. So I can just do box equals packmol on molecules. Maybe I want 30 molecules, and I want a density of 0.8. Yeah, then we have these 30. What I can do is I can write this to an XYZ file, for example, and then just open it in AMS input. And then I have it in AMS input and can work with it here. So let's just run a short MD simulation. So I will do job equals AMS MVT job on this box. And actually first I need to specify the settings. So settings.input.forcefield.type equals UFF. Right? Settings name MD, temperature, let's run 300 Kelvin, let's run 500 step with a 0.5 femtosecond time step. And let's just do job.run. So this shouldn't take very long. And okay, it's successful. And now if I do RKF equals job.results.RKF path, then we can find the path to this RKF file, which contains the trajectory, and then I can just open it in AMS Movie. Anyway, that was just a quick example of what you can do with the Python interface. And you can, of course, also do much more with it. So these are then some of the things that I was mentioning during this talk. And if you want to use them, sometimes you have to buy a special license for it. So yeah, you can find that on this slide. We're also on our website. Finally, then, yeah, I want to thank all our academic collaborators, partners, and contributors for this release. This is not a complete list of people who have contributed for previous releases. There are also many more. I hope I didn't miss any name here. But yeah, many people implementing a lot of new functionality, and I haven't covered all of it in this talk. So to summarize, yeah, we released Amsterdam Modeling Suite 2023 in April. Some of the highlights include the heterogeneous machine learning potential, the AMP polarizable force field, the quasi-particle self-consistent qsGW-BSE, and the ParAMS multiple optimizers and sensitivity, and much more that I hope I covered in this talk. And you can find the full release notes at scm.com/2023. So that's the end. Thank you for your attention. We have some links to the release notes. If you want to get a free trial, you can get a free trial for our software. And we have a YouTube channel where we give these types of webinars, also tip of the week videos and so on. So now I'll be happy to answer questions.